Detecting the most elusive substance in the universe requires a laboratory that spans billions of miles. We are currently living inside of it. The target is dark matter, the invisible gravitational glue that holds galaxies like our Milky Way together. One of the leading suspects for this missing mass is a swarm of primordial black holes. These are incredibly dense objects that formed fractions of a second after the Big Bang. Hunting for ancient black holes presents a unique challenge. They absorb light completely, which makes them impossible to photograph. Traditional astrophysics relies on capturing photons or radiation, like radio waves or visible light, but standard telescopes cannot track something that leaves no visual signature. To find an object that swallows light, we have to look for its footprints. We need a detector that can measure the gravitational wake a black hole leaves behind as it moves through space. Physicist Sohrab Rahvar realized that the solar system already functions as a giant gravitational sensor. We just have to learn how to read its data. The outer edge of our neighborhood is wrapped in the Oort cloud. This is a spherical shell containing roughly 1 trillion icy planetesimals and comets, orbiting at massive distances from the sun. Think of this cloud like a set of cosmic wind chimes. We cannot see the dark matter wind blowing through our galaxy, but if a heavy object passes through, the movement of the icy chimes gives it away. When a primordial black hole drifts through the Oort cloud, its gravity yanks icy objects off their orbits. Some comets are ejected, breaking free into the void. In other cases, it steals the comet's momentum, causing it to plummet inward toward the inner solar system. The Oort cloud is a billion-year-old gravitational tripwire, wired to send a signal, in the form of a falling comet, directly toward Earth. This giant tripwire has been running since the dawn of the solar system. By looking at the current state of our neighborhood, we can see how often these gravitational kicks are actually happening. The first data point is the survival of the Oort cloud itself. If the Milky Way was packed with stellar mass black holes, their constant disruptions would have emptied the cloud of its comets billions of years ago. The second data point is written into the ground, Earth's geological crater record. This chart compares predicted impacts against evidence. The red line shows comet strikes if black holes were all dark matter. The flat blue line is Earth's actual record. Since Earth wasn't pulverized, primordial black holes make up at most 0.1% of missing mass. The quietness of our skies is a scientific result. It means the majority of dark matter must be something other than heavy, compact black holes. Even if black holes are only a tiny fraction of dark matter, a few may still be out there. To find them, we have to look for a specific pattern in the wind. Our sun drives forward through the galaxy at 220 kilometers per second. While you might expect a headwind of comets from the front, gravity works differently. A black hole passing us head-on moves too fast to impart a kick. But a black hole catching up from behind stays near the Oort cloud for much longer, giving its gravity more time to work. This creates a 13-to-1 ratio. For every one comet arriving from the front of our path, 13 should arrive from the rear. It's a directional sneak attack that only a heavy passing mass could cause. We will soon have the hardware to scan for this pattern. The Vera C. Rubin Observatory will map millions of objects and track the exact origin points of thousands of new long-period comets. If the observatory detects that 13-to-1 rear-side bias, it will confirm that a hidden population of primordial black holes is drifting through our neighborhood. The Oort cloud is more than a relic of the early solar system. It is a live record of the invisible forces shaping our galaxy. Watching how it moves allows us to weigh the darkness of the universe. To see how we're mapping the rest of the cosmos, subscribe for our next deep dive.